So one of the questions was about want to start with the Lewis stuff, or yeah, okay. So your question about the dots, are you asking when you draw a Lewis structure, or when you just draw the Lewis dot symbols? So like if you had something like carbon, for example, right? And carbon is group 4, I think. So is your question, can you do like this deal? Or can you like kind of do that deal? Truthfully, to me, it doesn't matter. I don't think so. As long as you don't really go more than 2 dots per side. I will say most people will sometimes kind of go clockwise and kind of do 1 dot at a time and then kind of go back and start pairing them up. That's just sort of a common way that people sort of do it. But really, as long as you have the right number of dots there, it really doesn't matter, unless you find somebody ultra picky. But I will say in general, most people will a lot of times just kind of go around and then maybe just start pairing up things. But again, really the main rule is just not to really go over 2 on the side is sort of the main rule on that. I'm gonna say, was that in those chapters? It's been so long, I'm not even sure what chapters those are in. It wasn't. So this would be more, I think, exam 2 stuff, I think, right? That was, I don't know. Like, that's gonna just put those 2 exams together at this point. I'm not sure. So you might be in trouble. I might write the wrong exam already at this point, but okay. So it might have been maybe in 4 at the end, maybe. It might have been. I don't know. Could have been from an old edition. I think it might have been. I would say I think in this book now, where that's like chapter 6. Is that chapter 6? Yeah. Yeah, it's chapter 6, I think. To answer your question, it should be on this exam. But that would be how you would do it when we come to exam 2 for sure. So that should be exam 2 stuff. I think that sometimes they do. Sometimes I think it was covered very briefly, maybe in chapter 4, maybe like really briefly, I think. But we really kind of put it into use into chapter 6, I think, is where we did it. Because I think in chapter 4 was chapter 4 is was chapter 4 electrons too? Chapter 4 is electrons, I think, right? And usually with electrons, we talked about valence electrons, and usually around that time, sometimes we talk about the dot symbols and stuff like that, which is the valence electrons to show it. But then really the main use of that would be with Lewis structures. Other questions was, you said something about balancing, is that one, or heat of fusion, either one? Yeah. Hang on one second. Yeah, go ahead. Okay, we'll do a heat of fusion first, and then we'll do some balancing. How's that? So is your question on heat of fusion, what it is, how to use it, or that type of thing? Yeah. Yeah, so there's basically as we transition from sort of one phase to the next, for example, we draw a little curve here. And we'll say this is safe for water. So if this was water, this would be about 0 degrees Celsius. This would be about 100 degrees Celsius. And basically what we would have going on here is this would be basically ice, which is really, right, the solid version of water. This would be liquid water. And up in this region here would be steam, which is basically the gas version, right, of water, basically. And the transitions, when a substance transitions from, say, solid to liquid or liquid to solid, there's a certain amount of energy required just to do that transition. And that transition occurs at the same temperature. And for example, for water, it's 0 degrees, and that's the normal melting point or freezing point. where that occurs. And as we transition from liquid to gas, that happens at 100 degrees Celsius, which is the normal boiling point typically of a substance. And it happens at the same temperature, those transitions. And really, when we are at those sort of transitions here, we actually have both phases happening at the same time. So at exactly 0 degrees Celsius, for the case of water, you actually have kind of like ice crystals. So you got some solid happening, you got some liquid water happening. And it's really not till you get a little bit above 0 degrees Celsius that you actually kind of transition really into water, liquid water. It's not until you're a little bit below 0 degrees Celsius that you actually transition into ice. And the same thing happens up in this region as well at exactly, say, 100 degrees Celsius. You have basically liquid water and kind of like steam or, happening at the same time. That's actually what happens at the surface of any sort of liquid. There's always stuff that's basically jumping out into the gas phase, and there's stuff that's going through condensation and dropping back into the liquid phase at the surface of a liquid. And again, it's not until you get a little bit above that 100 degrees Celsius for water, for example, that you do get into sort of the gas phase, and a little bit below that you're still in the liquid phase. So there is an energy to basically take a substance like water from like water that's a solid to water that is a liquid and backwards at 0 degrees Celsius without changing the temperature. There's a certain amount of energy required just simply to do that transition, take it from one phase to the next. And that is what is referred to as the heat of fusion when we do that transition. And the heat of fusion is sometimes abbreviated delta H of fusion. The delta H is what is referred to as the enthalpy. It's a fancy word for heat, basically. So that's a fancy word for basically the heat that's required to do that transition. Now, as we go from solid to liquid, it is a endothermic process. You have to put heat and energy in to do that. And that would mean that the energy value, our number, would be a positive number, which is usually what positive energy values mean. It's an endothermic process. Energy is absorbed. Going the opposite way, when we have liquid water, we actually have to release the energy from the liquid water, because in liquid water, it has enough energy to kind of move past each other, which is why liquids are fluid, right? We pour them and stuff like that, because they have enough energy actually for the molecules and stuff to kind of move past each other. So as we release the energy from liquid water, they actually begin to sort of lose the ability to kind of move past each other. And now they kind of lock themselves into basically the solid phase as we release the energy. So going the opposite way from liquid water to solid, that is a negative value, which is basically an exothermic process. And that means that energy is released. Now, for specifically water, the value for the heat of fusion for water is approximately 333 or 5, I forget which number, but it's really around 333 or 35 joules per gram. And they may use calories in your book, right? And the relationship between a joule and a calorie is 4.184 joules is equal to 1 calorie. So roughly speaking, if we use 333 number divided by 4.184, it's roughly about 79.5 or about 80 calories per gram to do that. So roughly about 80 calories per gram. And that is basically the heat of fusion. And that is the energy required to basically change a certain amount of water in the solid state to liquid, are going the opposite way. We have sort of the same situation that happens up here, but this transition is what is referred to as the heat of vaporization. and also sometimes referred to as the delta H, okay, delta H of vaporization. And that is also the energy required to do nothing more than take liquid water at 100 degrees Celsius and turn it into basically gas at 100 degrees Celsius, not change the temperature, just simply take it from one spot to the next. And that would be this sort of transition going from water in the liquid phase to water in the gas phase, which is steam, are backwards. So that's basically evaporation going to the right and condensation going to the left, basically, is what's going on here. It's the same idea as we go from liquid water to gas. That is an endothermic process. You got to put the heat energy in there. When you do, the liquid water gains enough energy and they start to basically go away and start to boil, basically, and go into the gas phase. Exothermic for going from gas to liquid, because gas molecules are flying around. So as you remove the energy, what happens is they slow down. And when they come in contact with each other, they don't have enough energy at that point to escape each other. And they kind of clump together, fall into the liquid phase, for a lack of a better description. Now, for the delta H of vaporization specifically for water, that's about 2,260 joules per gram. And if we were to convert that into calories, because I think your book likes calories for some reason, something like 540. Yeah, that's not too bad. 540 calories per gram. So what we do with these numbers, and we'll put our other guy up here as well, that we just talked about. Is if your book used to, it ranges. What's the book now? No, I'm just kidding. I'll be honest with you, it ranges anywhere from 333 to like 335. So it's in the same ballpark. So if you like, I'll use the number that's in the book. Is it 334 in the book? Yeah. Just like the 2260 ranges depending on the book. So they do kind of range a little bit depending on the calculation that's done. So if we were to want to figure out something like, for example, if I had, 600 grams of ice cubes and I want to know how much energy was needed to melt them, right? So if I had something like, I have 600 grams of ice at 0 degrees, how much energy is needed to melt them? It's a liquid water, basically, right? At 0 degrees Celsius. We would want to use at this point our heat of fusion, because that's the transition that's going to happen. We have ice that's solid, and as it melts, it will make liquid water. So that's the transition from solid to liquid, which would be the heat of fusion. And it really just becomes like a conversion problem at this point. Our mass here for our ice is in the correct units, is grams, and we'll use the calories since your book likes it. So we'll do 600 grams of ice, right? And to do that transition, it requires 80 calories per gram. The grams will cancel if we multiply 600 times 80. We end up with 48000 calories is needed. This would be a positive number, right? It is endothermic, so that's what that number implies, and it is correct because it is a positive process here that's happening. What would happen if I took the same 600 grams of liquid water and wanted to turn it into ice? What would be the only thing that would be different in the calculation? It would be negative because it's an exothermic process. So if we started with 600 grams of liquid water, we would use the same value, because it is the same value no matter which way you go. But in this case, it would be an exothermic process. So we would make that 80 negative. and we would end up with really the exact same number. That's sort of the conservation of energy. What was that number there? Minus 48000 calories. The only difference here is it's negative, so it implies that it is exothermic, and that energy needs to be released to allow those liquid water basically to become ice cubes. So, any questions on that there? Was that your question about that stuff? Yeah. Okay. Other questions I can answer for anybody? No. All right, so you want to do a little balancing here, and perhaps let's see. Equations, huh? All right, let's see. Let's do. Okay, let's take a look. So once again, on the top one here, we do have some polyatomic ions. So as we talked about earlier, again, you can go element by element, but it is sometimes easier to kind of keep those guys together. So here I do see a sulfate, and I do see a sulfate over here, and I do see a hydroxide and also a hydroxide that looks the same on the other side. So on this approach, I'm going to keep those together and just sort of balance those first to try to get me into maybe a good place. Once again, here you could try either of the polyatomic ions on either side to sort of start with. In a lot of cases, it may not make a big difference, but sometimes it will make a difference, sort of which one you start with. You might have to go back and maybe try the other one first. So in this case, if we wanted to, we could try the sulfate. On the left-hand side, I have one sulfate, right? On the right-hand side, I have two. So to fix that, I could just put a 2 in front of the sulfate on the left-hand side. That gives me 2 of the SO4s. And again, when you do this approach, you do just kind of want to follow your coefficients. So what I mean by that is, since I just put the 2 on the left-hand side there to fix the sulfate, it also now directly just changed the copper. So that's really where I want to go next after I do that. So I just got my copper on the left-hand side to 2, and my copper on the right-hand side is 1, right? So that is, again, sort of where I want to go next, is sort of follow my coefficient. I could go to the other side and put a 2 in front of the copper. When I do that, I now have 2 coppers on each side. That also will now change the hydroxide, right? That's going to be 2 and 2, which gives me 4. And lucky enough there, that is what I need for the other side. So believe it or not, I am done at this point. And you can see it kind of happens really quick. I see some surprise in the front row, but yes, you are done. It's over. And that's what I mean. So it's very much a lot easier to kind of keep definitely those polyatomic ions together. And that's essentially what will happen, is it should just sort of fall into place if everything is there in the correct formulas as you sort of put, 1 or 2 or 3 sort of coefficients in there. Everybody else just sort of fall into place. And again, what I did was, like I said, I started with the sulfate in this case. I put the coefficient, and then this gives me really my next direction is the guy that it changed to go to. And that again gives me my next direction. And so you just kind of want to keep following, as one changes, go to the other side and fix it when you kind of do that approach to balancing. Question on that there. For the bottom one, we really don't have sort of polyatomic ions, so I am going to resort back to a table, which is, again, a really good way to do it. It just sort of focuses you in on, what you need to do. So we have carbon, hydrogens, and oxygens. Left-hand side, we have 2 carbons. Right-hand side, we have 1. Left-hand side, we have 4 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. And on the right-hand side, we have 2 there, plus 1 more there, gives us 3 oxygens going on. Once again, you just go with what seems very easy to solve. And in this case, I see copper is 2 on the left and 1 on the right. So that seems a very easy thing to solve. So we could just put the 2 there. When we do that, that gives us 2 of the copper. We still have 2 of the hydrogen. And now in terms of our oxygen, we have 2 times 2, which is 4. Again, plus 1 more over here on the right. That gets us to 5. Now at this point, we fixed the copper copper. I always get to say that wrong. We fix the carbon would be the right element there. We fix the carbon. They all start with a C. You know, they're all like copper, I think. We fix the carbon, and we have an option of hydrogen or oxygen to fix at this point. At this point, I would go with the guy once again that is not in a lot of places. So when we look at the oxygen on the right-hand side, we got it in a couple of places, but when we look at the hydrogen, it's really just in one place, and that's probably the best place to kind of go after next. And we could easily solve the hydrogen here by putting a 2. That is going to get us 2 carbons. 2 times 2 is 4 hydrogens. And now our oxygens, once again, we got 2 times 2, which is 4. And now we have 2 times 1, which is 2. So that is going to give us now 6 oxygens, which we can obviously easily fix by going back to the left-hand side and putting a 3 there. And that then should get us our 2 carbons, 4 hydrogens, and 6 oxygens in that case. Question on those there. All right, let's try one. Let's try the one we actually skipped in the notes. See how we do on that one here. Why don't we try this one, which actually is from your notes, I think. NH3 plus O2. NO plus water. And while you're at it, why don't you do N2. Okay, let's take a look here. I'm gonna start with the bottom one first. Feels better. All right, so I'm gonna make a little table here. So we got NH. That's it. On the left-hand side, we have 2 nitrogens. Right-hand side, 1. Left-hand side, 2 hydrogens, and 3 on the other side. So again here, perhaps nitrogen would seem the easiest. Yes, I'm sorry. For the nitrogen, is there asking? Right here. So there's just 1 here. So remember, when there is really no coefficient written, it's assumed to be 1. So that's where that comes. Yeah. Other questions? Okay. All right. So we will start with the nitrogen, as it looks like it is probably maybe the easiest. We could just put a 2 in front of it. That will then give us, again, basically 2 times 1, which would give us 2. And once again, we do need to distribute this down to the 3 as well. And that would get us 3 times 2, which is 6 there for the hydrogen. That then tells us from our table that it is hydrogen where we need to go next, to the left-hand side. And we need to make that 2 into a 6. So we will need a 3. And that will do it, because that will be 3 times 2, which is 6. We still have our 2 nitrogens. And now we are balanced at that point. Yeah. Any questions on that one there? All right, then let us do the guy up there on top. So we'll make our table over here, perhaps. So we got some nitrogen, hydrogen, and oxygen happening. And on the left-hand side here, we got 1 nitrogen. Right-hand side, we also have 1 nitrogen. Left-hand side, we have 3 hydrogens. Right-hand side, we have 2 hydrogens, which is here and here. Left-hand side, in terms of oxygen, we have 2. Oh, sorry, left-hand side, we have 2. Right-hand side, we actually have 2 as well. I guess I was right there. We have 2 oxygens on that side. So it doesn't look too bad here, perhaps. So we basically have everything balanced except for hydrogen in this case. And really, we have 3 on one side and 2 on the other. So in this particular case, which sometimes does happen, we actually need to kind of put a number on both sides to start this here. And we obviously want to get to a common number. The common number between 3 and 2 would be 6. Basically, just multiply those 2 numbers together, right? So 3 times 2 is 6. And that means to get our hydrogen on the left-hand side, the 6, we actually need to put a 2 in front of it. And to get our hydrogen to 6 on the right-hand side, we need a 3 in front of it. So that's going to do some changes here to our table. So we'll start on the left-hand side with that 2 in front. That will give us 2 nitrogens. We then would take the 2, right, and multiply it over to the 3. And that will get us our 6 hydrogens, which is what we're shooting for. And we still have the 2 oxygens. On the right-hand side, we still have 1 nitrogen. Hydrogen, once again, 3 times 2 here will get us to 6. And oxygens, we are now up to 1 there, right? And once again, that 3 will also go for the oxygen that's here. So that's another 3. So that is 4 oxygens there on the right-hand side at this point. Any questions up to there? Probably the next easiest thing to do as we fix the hydrogens, but really screwed up everything else, which happens a lot when you're balancing things. The next easiest thing really to balance here is going to be the nitrogen. Once again, it's the nitrogen just by itself, really, and one thing on each side. So that makes it a lot easier to balance. We got oxygen all over the place, right? So that's a lot more complicated sort of thing happening. So to fix the nitrogen on the right-hand side, we're going to lay up a 2 here. And when we do that, that will then get us 2 for the nitrogen. That will get us still the 3 times 2, which is 6 for the hydrogen. And now for our oxygen, we have 2 going on there. And we still have the 3, which means we are up to 5 at this point. Yeah. Any questions at that point? All right, so clearly we put numbers everywhere but the O2 on the left-hand side. So that is where we're going to go next, because the one thing you do not want to usually do is start erasing numbers you put down, because then it's just going to be a really long evening. Yeah, so you can occasionally you might need to erase a number or 2, but you don't want to constantly keep erasing numbers, otherwise you'll never get anything done. So basically we're in this situation where we need 5, but we have 2 on the other side. So this would be a good place to do what? Yeah, this would be a good place to do a fraction. So once again, when we do the fraction, the top number is always going to be the number we need. So in this case, we need 5. So we would go with a 5 up on top, which is the number we need. The bottom number should always match that number there, which is a 2. And by doing that here, we will end up with, I clear out a little space, maybe. We kind of redo our count here, make another table. We got nitrogen, hydrogen, and oxygen. Left-hand side, we now have 2 nitrogens. Right-hand side, 2 nitrogens, so that's good. Check. Hydrogen, we got 6 on the left and also 6 on the right, so that's good. Oxygen, we have 5/2 times 2, which equals 5 on the left. And over here, we again have our 2 and our 3 oxygens, which equals 5. So once again, by using the fraction here, we did balance it. But should we leave the fraction? We should not. So now we need to get rid of the fraction. So we're going to multiply everybody, not just the fraction, but everybody in the equation by the denominator. And we will do that with a big bracket. And the denominator here is a 2. So we're going to times everybody by 2. When we do that, we end up with 4NH3 plus 5O2 gives us 4NO plus 6H2O. And all I did was just multiply the 2 to every coefficient that we had going on. And once again, if we do this, we should still be balanced. So we now have 4 nitrogens on the left. We have 4 on the right. So check. We got 4 times 3 for the hydrogens, which is 12. We have 6 times 2 for the hydrogen, which is 12. So check. And we have 5 times 2 for the oxygen, which is 10. And we have 4 oxygens here. And we have 6 more here, which is 10. So we are balanced at that point. Yeah. Question on that one there. So again, definitely this is a situation like we talked about where it commonly does happen. We got kind of like the elemental form of a diatomic molecule like N2O2, those guys by itself on one side, and then that oxygen and a couple things on the other side. So that's it is oftentimes a place where you might need to use a fraction. So if you get to a spot like that, you can use the fraction. You just got to make sure that you clear it when it's all said and done. Question on that? Anything else I can help anybody with? All right. If you still have questions, feel free to hang out. Otherwise, it was nice seeing you today. We will examine on